Okay, so today lecture is about how to identify the stable or the radioactive nuclides and with the neutron and the proton ratios. As we have already discussed the nucleus stability depending on the binding energy and the average binding energy. So if you want to correlate the stability of the nuclide, that is the average binding energy is the more appropriate term to define the stability as in comparative with the other nuclides. Now, today lecture is about if there are, let's suppose, two or more nuclides are there, and maybe I can give you the any of the two nuclides, or you can identify or you can get these nuclides from the literature. So how can you identify them? Either these are the stable or the radioactive nuclides. So this is very, very important information. That means you are looking at the neutron and the proton ratios, and then you can easily define either the nuclides are stable or the radioactive in nature. So before moving to the this chart, let's have a look on the graph. Actually, these are the all the nuclides which have been plotted in a graph, and this graph is about the number of neutrons and the protons. Again, because you are learning or you are studying the nuclear chemistry, and here the number of protons and the neutrons are the most important. So these two numbers are plotted over here. These are the number of neutrons on the y-axis and number of protons on the x-axis. So if you have a look on the nuclides, this is the line passing through the origin, and all these are the nuclides available in nature. And if you have a keenly looked at the graph, actually the graph is not complicated to be understand over here. And because we are going to discuss the neutron and the proton ratios or the atomic number or the number of the neutron. So what would be the ratio in case of the stable or the unstable? That means the radioactive nuclides. So look at the start of the graph from here to here. That means the nuclides, these are the actually in the black, these are the stable nuclides. So if you have a look at this graph from this to this point, around this is around up to the 20 atomic number. Here it is around 20 atomic number. So the ratio between the protons and the neutron is 1:1. Approximately it is 1:1, and this is written over here. So atomic number, when it is increasing from 1 to 20, the ratio between the protons and the neutron is the 1:1, and this is up to the atomic number 20. So when you are moving above this atomic number, so what is happening? The number of neutrons are more as compared to the number of the protons. So this is the established or the fundamental, or you can say this is the natural phenomena. Before atomic number, sorry, after the atomic number 20, the number of neutrons are more as compared to the number of the protons. So let's first look at the detail of this graph. And again, I have already explained for the light nuclide, that will lighter me up to the 20. That means the atomic number of the calcium. The neutron proton ratio is 1:1. That means the number of protons and neutrons are equal in most of the stable nuclides. As you can see over here, 1 to 20, because this is the line which is indicating the ratio between the neutron and the proton is 1:1. So it should be 1:1 if the nuclides are following this line. But what has happened over here? These are the natural nuclides, and these are having a more number of neutrons as compared to the protons after atomic number 20. So what is the reason behind this one? So when you increase the atomic number above 20, That means higher number of the protons becomes a source of the instability. Why? Because if there are more number of the protons, because the protons are having a positive charge, and there should be a more repulsions between the number of protons, so the nuclides become unstable. But and there are many nuclides which are having the atomic number more than 20, but they are the stable. So why these are the stable? So this is the natural phenomena, that means the God has created among all these nuclides. So in order to diffuse this Coulombic repulsion, that means after 20, or if there are the number of protons are increasing, so there is another way to decrease the repulsions between the number of protons. That means if you incorporate something, or you can diffuse some of the Coulombic repulsion with the other particle, and these particles are the neutrons. That means if there are the two positive charges, these are repelling to each other. If you put the neutron inside, that means this neutron helps to inhibit the repulsions between these two protons. So that's why this is the God has created the more number of neutrons as compared to the number of protons to minimize the repulsions between the protons. So this is the indirect way. The other you have already learned. This is the binding energy, or the average binding energy. That is another topic we have already finished. But here important is to understand this fundamental principle over here. And then thus, the repulsive forces get diminished or minimized, and the relative size of the nucleus increases. Of course, when there is an increased number of protons or increased number of the neutrons, of course, the size of the nucleus will be more. So these are actually the some of the basic principles we have defined over here. What is the relationship between the number of protons and the neutrons among all nuclides available in nature. And this actually the brief description we have defined. This is not complicated to understand, and these are the four basic points to understand this graph. However, our objective is to identify now how can you identify the stable or the radioactive nuclide based on this neutron and proton ratio. So this is the graph, and what important over here is up to 20 neutron proton ratio is 1, and up to 30, that means 21 to 30 atomic number, the ratio between the neutron and proton is 1.25. That means these must be the neutron, and proton is 1. That means 1 proton equal to 1.29 neutron. If this is the case, then the nuclide would be the stable. So this is the stability chart. Actually, if the nuclides are following this pattern, then they are stable in nature. Otherwise, these will be the radioactive. So by increasing the atomic number from 31 to 47, if the ratio lies between 1.4, then these are the stable. Otherwise, if it is more, then these will be the unstable. And similarly, above 76 nuclides, and these are the around 1.5 neutron and proton ratio, and the that means the nuclide would be the stable if they are having the ratio 1.5 or less. So 1.5 or less, these are the stable nuclide. If it is increasing 1.5, then that would be the radioactive. So this is a very brief description to understand the neutron and the proton ratio. Now I'm going to use the whiteboard to do some sort of the exercise to identify the radioactive or the stable nuclide. So you must note all these values. So because based on this one, we are going to differentiate whether the nuclide are the stable or the radioactive. So let me start the exercise, and I'm taking as an example, let's suppose this is the example of the manganese, Mn, and this is having atomic number 25, okay, and the mass number is the 57. So now your objective is to identify this nuclide is a stable or the radioactive nuclide, and there is no lot of the calculation, just you have to calculate the number of protons and the neutron, and and later on you have to get the value of the ratio between these neutron and the proton. So there are atomic number 25, that means protons are 25, and the number of neutrons are that means 57 minus 25, and you would get the value from here, that is the over here is
32.
32, but this is the number of the neutron. Okay, now very simple, this is the actually we are going to calculate the proton, sorry, to calculate the ratio between the protons and the neutron. This is the ratio, how much, this is the 25 and 32, you have to divide with the lowest value, and again you always divide with the protons because we are taking at the neutron and the proton ratio, neutron divided by the proton. So this is 25, and this would become also 25, and you find out the ratio, that would be 1 is to 1.28. So this is the actually the important over here, and now you can define, actually this we have calculated, and always say there should be one proton, actually the ratio was this is the detailed description, 1 is to 1.29, and this is the neutron divided by the proton, neutron proton ratio, what has been described in the chart. There are only 4 values, and you have to remember these values because these will not be given to you, and of course you must remember all these 4 values. So now the ratio of neutron proton is 1.28. So what do you suggest based on the table? Either this nuclide, manganese 2557, is the stable nuclide or the radioactive nuclide? Anyone can give me the answer?
Stable.
This is the radioactive nuclide, and radioactive nuclide means radioactive. Okay. So why it is a radioactive? Because now the atomic number is 25, or you can say the number of protons are 24, 5, and you have already learned if the atomic number is up to the 30, and then the ratio between neutron and the proton must be 1.25. So this is you have taken from the graph we have already discussed. So this is the 25. 25 is below 30. That means 21 to 30 atomic number, the nuclide must having the ratio is 1.25, and this ratio is greater than 1.25. That's why this is the radioactive nuclide. So this is as simple as you can calculate the nuclear stability, either the radioactive or the stable nuclide. So let me do another example. And this is the, let's suppose, gallium, and gallium having the Ga, atomic number is 31, and mass number is 41. So calculate and let me know Just raise your hand when you finished. Either this nuclide is radioactive or stable in nature. So again, the number of ratio, you are just calculating the number of the ratio between the protons and the neutrons. And here the number of protons are 31. And how many neutrons? This is 71. 71 minus 31, that will equal to 40. Good.
40.
So the ratio again, proton is to neutron. The ratio, that means these are the 31, this is the 40, and you have to divide by both 31 and the 31. The ratio will be 1 is to, so again, 1 is to 1.29. Okay, so this is the ratio you have calculated. This is the gallium 3171. Now, what is the actually the final statement over here? You have to compare this one ratio and look at the value. This is 31, and we have previously we have decided when atomic number is up to 47, or 47 mean 30, we have already decided this is should be 31 to 47. So the ratio would be the 1.40 in this case. So now you have to compare just this ratio. This ratio is less than 1.4. That means this should be a stable nuclide. So this is the answer of this one. So again, only the we are considering only the 4 values, and you can consider that particularly the ratio, and you have to compare this your ratio. If it is less or equal to up to this one, then the nuclide would be the stable, otherwise these would be the radioactive. So let's do another example, because this is very important and very simple information you are getting over here on this lecture.
Excuse me, sir.
Yes.
Can you?
So another example is the potassium, atomic number 19, mass number is 37. And now do yourself whether this nuclide is radioactive or stable in nature. Actually, this is a special case. And as you remember what I have explained at the start of the lecture, so the ratio up to 20 is 1 is to 1. And there are number of neutrons are always greater than the number of the protons. So let's do first with the exercise, protons and the neutron. And here protons are 90, and how many neutrons? 37 minus 90,
18.
18. Good. So the ratio, again, in this case, I don't think there is a need to calculate the ratio, and I'm going to describe over here. So in this or in such type of the cases, there is no need to calculate the ratio, because ratio we are going to calculate it is the neutron over protons, and neutrons are always greater than the protons if there are the more stability, and if and then you can compare this ratio with the table what we have already discussed. But this is the special case. Why it is a special? Look at the values over here. Protons are greater than the number of the neutrons, and this is the first point in the graph which I have described earlier, so maybe you can watch again. So up to 20, the ratio between protons and neutron is 1 is to 1. And if you find the ratio of the or the number of protons are greater than the number of neutrons, then it must be a radioactive nuclide. And in this case, you do not need to calculate the ratio and to find out the stability by comparing the values in the table, which I have already explained. So if this is the first point, if the number of protons are greater than the number of neutrons, that means there must be a greater repulsion between the protons, and due to the less number of neutrons, there is no intermediate over here to reduce these repulsions, and the nuclide would be the radioactive nuclide. And what we are discussing in the previous exercises, where the number of the neutrons are greater than the number of protons. So your chart is what I have mentioned over here. This is the ratio, one ratio of the proton with the neutron proton ratio. It, 1.25, 1.4, 1.5, what we have already mentioned in the table. So this is the actually the final conclusion I have made over here. If the number of protons are greater than number of neutrons, then it must be a radioactive. And in the reverse case, when the number of neutrons are greater than the protons, then there is the confusion whether the radioactive may be stable or may be the radioactive. So you have to check the stability by comparing the values given in the chart. And this is all about our today lecture over here. Again, maybe you can, because I have only 2 minutes to finish this meeting. So the element tellurium having the atomic number this and the mass number this, that means these are the different isotopes of the tellurium, and then uh, its ratio is varying. I have already calculated. That means starting with the first one, ending with the last one, and then it is the ratio is between 1.35 to 1.5, and you can do at home. And in the next class we will discuss these in detail. And you have to identify among these isotopes which are the stable and which are the radioactive nuclides. And in similar case, there are the two elements of the antimony, two nuclides are there. And this is, I just have calculated, but you can do yourself. And neutron proton ratio from this to this is 1.37 to 1.41. Which one is the stable and which one is the radioactive? So this is all about our today lecture.